Good afternoon. I've really enjoyed today, and hopefully we'll be able to share with you a project that's got a little bit different goals than some of the things we were looking at earlier today. We're going to be talking about a project we worked on in outside of Istanbul in Turkey, the Pertev Pasha Mosque, where we were documenting this mosque as part of a broader efforts for planned conservation of the city center of Izmit, as well as several other mosques in the region. When we started this project, we sort of established a few goals, and one of them was, what can we do to document this mosque very, very quickly with a great deal of accuracy and using standard technology? We didn't have the ability to carry in large pieces of equipment. We didn't have high-end computers. And we wanted to do this quickly, cost-effectively, and we wanted to create a 3D digital model. Ultimately, as we'll talk about a little bit later in the presentation, the goal became to turn this into a virtual environment. So we were able to turn this into a VR environment. Unfortunately, we'll have to see that on a monitor, because to bring all the rest of the equipment to create that virtual environment was a little bit overbearing. The idea of 3D documentation, or this idea of photogrammetry, isn't anything new, and it's been around, as we heard a little bit earlier, for quite a number of centuries. But it was really in the 19th century that it took hold, and with this idea of overlaying multiple photographs to create a three-dimensional model of an object. Whether that be something that's interpretive, whether it's something that's developing precise sort of a metric photogrammetry where you're presenting precise measurements. And this was relatively the same processes that we were using even when I was in the school in the 80s, where we were doing stereo photogrammetry, overlaying two images to create a three-dimensional object. And it's really not until the late 80s into the 90s that we start to get into the digital technology. But even then, it was really dealing with sort of overlaying two objects and then tracing or creating a two-dimensional drawing from this idea of photogrammetry. One of the biggest significant developments that we have right now, and we've alluded to it in several of the previous presentations, is this idea of using these photographs to develop a highly accurate three-dimensional digital models, and doing this through a series of two-dimensional photographs. And the idea of this, what we call convergent photogrammetry, of these multiple viewpoints that can be correlated to create a three-dimensional representation. So fundamentally, what we're talking about is two algorithms in contemporary 3D photogrammetry. The first one is what we call a structure from motion algorithm, and the second one is a multi-view stereo algorithm. So the structure of motion algorithm takes a series of photographs, or takes a photograph, and based on the lighting, based on the physical parameters of the image, will determine the physical characteristics, the geometry of the camera, and the location of the photograph relative to the position of the object. When you take multiple views and multiple photographs, it will then sort of construct this three-dimensional matrix which will locate where each of those photographs were taken from, and then it can start to stitch together common points within each photograph to create a geometry. So based on sort of that framework, that matrix that's developed by the structure from motion, it then uses the next level, which is a multi-view stereo algorithm. What the multi-view stereo algorithm does is it looks at the color, the shadowing, the lighting parameters of the photograph, and it comes up with the most likely three-dimensional shape that explains the photographs that were taken. Now these have been being developed for about 10 to 15 years, and just in the last, say, 3 to 5 years, they become extraordinarily sophisticated and very, very accurate. So the fundamental process when you're dealing with photogrammetry and you're dealing with creating this three-dimensional shape is you're going to first collect your images or your photo sets. You're going to the computer algorithms will compute the parameters for each camera image. It will next create this matrix and finally construct a three-dimensional form based on that set of images. But it's also important to note that the accuracy of this final three-dimensional model is only good as the quality of your images and the number of images that you use. So if you're using a cell phone and you can only upload maybe 40 photographs, you're not going to get as accurate versus some of the software that was mentioned earlier, which sort of has these, for practical purposes, no limit to how many photographs you can upload, and the level of detail you can get is obviously relative. So there's a lot of software out there and a lot of applications. So when we're thinking about this, we're not creating software, we're just trying to think about how we can use that within sort of our cultural heritage documentation and interpretation. So there's everything from the simple cell phone applications that you may see all the way to some much more sophisticated software. And these are changing all the time. For example, the Autodesk 123 is a very common one. It was very appropriate for, say, your cell phone or some very simple photogrammetry. I think it had a maximum of about 40 pictures for your cell phone application, 70 for the desktop. And we just got an email within the last few weeks that says they're going to be phasing that out.
It's discontinued.
So actually, by March 31st, that it's been phased out. So you can still mine your data, but you're not going to be able to create that, right? And that was sort of a staple. A lot of people were using that. When we started our project, and we were in Turkey, we were using Autodesk Recap Photo, which is a little bit more high-end. You can get up to about 250 photos per photo set. That was good till about last year. Now they've remorphed it, and it's become Autodesk Remake. There's a little bit differences on how the interfaces work. You have to download an application to your computer. It's not all cloud-based. And then you have your options for cloud-based versus a local processing of your data, which can have some advantages or disadvantages depending on how you want to work at it. So there's a variety of different methods. We're using SLR cameras to collect our data. We're using Autodesk Remake, which does have some limitations of 250 photos per photo set that it will work. But they're also like I heard earlier mentioned the Agisoft Photoscan, which is a little bit more powerful. It can use many more photographs in their photo sets and get larger models created. Once we use this, we process these photos. So we've collected our data. We've processed them into the initial three-dimensional physical or digital model. We then go through a series of post-processing refinements where we actually have to manipulate that model to make it accurate. There's a lot of distortions that have to be corrected. There's some geometries that can be simplified. There's some geometries that can be overlaid as well. And it all depends on what that final use for. And we'll go into a lot more detail of that a little bit later. We're using Rhino. We're using Autodesk Maya and Mudbox. So Maya is a 3D modeling. Mudbox deals more with surfaces, and then also sometimes they've been getting into using some makerware. So I'm going to talk a little bit about the mosque to give you some perspective on what we're presenting today. So we're at the eastern edge of the Sia Marmara in the town of Izmit. So this project, our data collection all happened in September of 2015. We were part of a partnership with Kocaeli University in Izmit, Turkey, that had this large project funded by the Scientific and Technological Research Council of Turkey, known as TÜBİTAK. So we were looking at a series of mosques as well as some urban centers surrounding these mosques. So Kocaeli, the region of Kocaeli in the city of Izmit has a very, very long history. It was first settled around 1200 BCE. Became very prominent during the Roman period. In fact, it was one of the 4 regional capitals during the Roman times. During the Byzantine area, it kind of fell off as importance as Constantinople rose to importance. It got a lot of different people came in. There was a lot of raids, a lot of destruction. So what we see from the Roman period really is pretty minimal. Again, during the Ottoman era, it grew to prominence, and it sort of gained that prominence, continues with that prominence today. It's really a gateway city, so it's a gateway between the ports and the roads for trade traveling east to west and vice versa. It did go through some serious earthquakes. There's been a lot of serious earthquakes there. But the most recent one was in 1999, and that's what sort of prompted the initiative that we've been part of. The mosque itself was built in the 16th century, in the latter part of the 16th century, and was part of a larger complex that included a mosque, a poorhouse, travelers' lodging, a bath, school, market, fountains, and a kitchen. Today, really only the fountains and portion of the school remain, as well as some of the walls and gates and the mosque itself. The interior of the mosque is what we're going to really be focusing on today. We did look at both the interior and the exterior, and we'll talk about at the very end some of the challenges that we had with that, dealing with the photogrammetry. But we focused mainly on this room called the Musalla, which is the prayer hall. And focus on documenting the prayer hall. There's a lot of unique features and there's a lot of commonalities, and these become very important in how you process the data and what we need to ensure that the 3D documents really are accurate. Some of the things that you'll notice that are important is you've got the band of calligraphy that on first glance may look very similar, but it's all got unique lettering and unique text, which becomes critical in trying to match up those photographs. You'll also notice that we have what are called squinches, which are these 4 half domes at the 4 corners of the building. And again, those become very critical that inside there's decorative calligraphy in those as well. And that became a critical component in how we were able to match up and how the software was able to accurately create the model. So with that, I'm going to turn over to Chris, and he's going to walk you through some of the processes that we went through and some of the captures that we were able to create.
Sure. Yeah, so as we kind of got into the photogrammetry process, we broke it down. One of the other goals while we were there was to teach them a documentation method, to teach the students a documentation method that they can take with them. So we had to achieve that from start to finish, including an example project within a week. So photogrammetry suited itself pretty well to that, whereas something like laser scanning is a lot more intensive, time intensive, both to capture and then process. So photogrammetry lent itself pretty well. And so this was kind of an example of, we went out and I sketched the mosque and its grounds, and then we assigned some different smaller portions. We made what was ultimately an unsuccessful attempt to capture the outside of the mosque that was hindered mostly by a lot of trees. That made it difficult to ever get any decent matchable photographs from various vantage points. So we broke the process of photogrammetry down into 4 pretty succinct steps. That is, you plan your campaign, you capture your photos, you process it, you send it to whatever software program you're using, and then optionally there's extra post-processing you can do. And for us, for the mosque, that didn't really end up happening until well after we returned back to the States after the trip. And then, of course, depending on the size and complexity of the project, you can repeat those steps as many times as you'd like. Kind of indicated here, you can see we plan to break down the porch and the sides and the outside of the mosque into separate campaigns, just due to the limit of photographs you can submit at once. And then the idea would have been to combine all of those completed photogrammetry models into one supermodel. So something very similar to the laser scanning method, where you do multiple scans and then combine them later. And I'm sure a lot of you are already very familiar with the photogrammetry process, so I'll try to keep it brief. But for those of you still learning, we taught them a lot of the basics of how to do a photogrammetry campaign, and kind of the golden rule that that we've kind of discovered along the way was that you need to always minimize the number of inconsistencies that you have, whether that's your camera settings, whether that's controlling the subject itself. Whatever you do, try to minimize any sort of change that happens from when you take your first photograph to when you take your last one. So like here's your exposure settings. On one side you've got something kind of overexposed and then underexposed. And so then, you end up with the problem of one picture looks like a black and blue dress and the other one it's white and gold. And then everyone gets in a big fight and the software gives up and it goes home. The other one is shadows. So like here I kind of intentionally leant over, got in the way of a light. You create the shadow that creates an artificial point that the software might try and latch on to, say, oh, this is a point, let's look for it in other pictures. Can't find it, so it gives up. Same sort of thing would happen on a really large building on a cloudy day or a partially cloudy day when you've got clouds moving in and out, you've got shadows that are appearing and disappearing. So again, try and minimize that. Either shoot on a day with full sun, or ideally when it's overcast is actually your best conditions. The second thing to do is to determine kind of the two basic methods of capture. One is inside out, one is outside in. Outside in is when you're looking inwards at a sculpture, and you can get around the outside of it, and everything is, it generally ends up being a convex shape, more or less. And then inside out tends to be a little more complex of a capture method, where you have to, I think the best method that we've developed so far is to move around a space that you're trying to capture the interior of, or something that wraps around you, and move from spot to spot, taking lots of panoramic pictures, just kind of sweep, blast your camera all over the place. And the method that kind of the analog that I kept trying to tell them was kind of imagine like you're spray painting, and you want to put multiple coats on everything. So you can see this wall from here, now go over there, paint it, move over there, paint it, and keep moving on until you've seen everything a few times and covered it with multiple coats of paint. For the mosque itself, the method that we used, actually most of the mosque was captured in one very quick round. The first day when we were just touring around the entire site, the multiple mosques, we were able to enter the mosque and access only that balcony. And so while we were there, our tour guides were telling us about the place, and I was moving around in between, and from these 6 points along the balcony, you've got these kind of 3 balconies, and I stood at either end of each one and just did a low pass, a mid pass, and a high pass looking into the mosque itself, just kind of on a whim with a little bit of planning, but then processed them overnight and then had a model that was effectively the floor, the back or front wall, the 2 sides, and most of the dome. So that was almost 80% coverage of the entire interior of the mosque just on one very quick photo campaign. Yeah, I guess, so that was actually entirely captured out of just 129 photographs. That was done in, I would say, probably about half an hour. And then a couple days later, we were allowed to come back and access the entire mosque. So this is looking essentially from the vantage point of one of those balconies and showing all the other photo locations that we were able to get to, including the minbar. They were able to climb the steps and get some high vantage points from lots of different angles. That was very advantageous. And then capture back towards the balcony that, of course, you can't capture when you're a part of it. So this is just kind of a look at the interface of Autodesk Recap as it stands right now, because as we already mentioned, it's a very dynamic field. So the interfaces, the entire programs themselves are constantly changing. So this is kind of an optional registration step where you can capture, once you have all your photos, pick 2 different pictures, and then identify manually various points that show up in different pictures. These are 2 different pictures, but we've identified where the railing meets this post, the top of this arch, and the bottom corner of this doorway. Identified it in 2 photographs, and then you can manually do that through all 250 photographs with multiple points and end up with countless dozens of points, just to kind of give the 2 algorithms a helping hand to get them started. And then that's kind of the finished product, what it looks like in Recap. Keep up with my notes here. And so as Jonathan mentioned earlier, one of the unique advantages we had that lent itself, it was a very lucky coincidence almost, was that the style of ornamentation in a mosque is always calligraphy, and they do different calligraphy all the way around, which to someone who does not read Arabic, it all looks very similar to me. But when you look at the geometry of it, it's highly variable, which creates essentially a tracking target for the software to latch onto. And so this is kind of a close-up example of those 4 squinches. So there's the calligraphy inside the dome, and then these 2 spots also on either side of each dome. And each one is unique, so that when you captured a photograph that partially contained one of the squinches, the software was able to identify which dome. Because as you look at the mosque, the bottom has a bilateral symmetry, so either side reflects itself. When you get up to the level of the squinches, you've got 4-directional rotational symmetry, and then when you get up to the dome itself, it's completely identical in 24 different directions from a geometric standpoint. But once you add the texture and the visual component, then there's actually some differentiation to identify which way you're looking. And so again, as we mentioned, there's the other goal that kind of developed out of this was, in addition to capturing accurately, we also wanted to have this as an experience that we could bring back and give to other people without having to take them to Turkey, because that obviously gets cost prohibitive very quickly. And so what we had to do then was start to simplify the model that we had. And so after processing the mosque and having the entire model, we decimated the mesh, which is essentially reducing it to try and preserve the overall shape, the overall form, and any substantial changes, but at the same time trying to eliminate any duplicate meshes or lots of detail in places where it's completely unnecessary. So like you can see, this was our original mesh, which is very, very dense, and then that was the final mesh that it was decimated down to, and then there's the associated texture maps above. So the original one was pretty detailed. You can see a slight loss of quality, but it was still enough so that you could see the detail in the calligraphy and the overall impression of what the space was like. So the original model was 252 megabytes and composed of about 11.8 million polygons, but once it was remastered into the lower optimized version, it was an 8.9 megabyte file that was made up of only 340,000 polygons. So then one of the processes that we went through, this was something that a GA in my lab did, was created proxy geometry. I think it gets back to the Solman presentation of, what is the accurate thing and what is the intended thing, and where do you draw that line. And when you're doing, trying to optimize something for virtual reality or to run in a live rendered view on a computer, you're going to want to trend towards maybe less accurate, but more of what the intent of the design was. So here you can kind of roughly see the highly dense dome mesh that was created, and then in red, a proxy geometry dome that is an actual sphere versus the rough kind of modeled look of the photogrammetry capture. But more importantly, you can see how massive those mesh faces are versus the original mesh. So that's, you know, just one example of the many different spots where the model was kind of carved up but then replaced with something that was nearly accurate, but more importantly, much less heavy from a computer processing standpoint. There's just another view of it. And then the other thing, in addition to reducing the geometry, is also reducing the texture maps of the model itself. On the left side, you'll see kind of one of the raw texture files that comes out of photogrammetry. If you've ever dug into a photogrammetry model, you'll probably recognize the very haphazard quilt work that is one of those texture maps. It's just very perspective-based and kind of random. But then on the right was the remastered file that our GA processed. And so everything is kind of chopped up a little more logically. The larger areas get more presence, the smaller areas get less. Like the floor area was completely repainted, essentially. He took it into a combination of Mudbox and ZBrush, and straightened out some lines, kind of evened out color tones and all of that. So then we'll go to a live model here of what we ended up with. So you can see kind of the floors. We originally had a problem where it was kind of bumpy, but it was all leveled out, replaced with a flat mesh. A lot of these niches kind of were ballooned out because we didn't focus on them directly. So then from the outside, if we go behind the walls, they were replaced with very simple, just six-sided, well, actually just five-sided little cubes. And then out here you can just see the entire scope of the model and how everything was. I guess it would have been good to show the original with all the balloony stuff. But there you go. And then also for example, the chandelier was completely replaced and modeled by hand, because something that small and that detailed is, of course, a very poor candidate for a photogrammetry campaign. So that was recreated. But then additionally, for virtual reality, the other consideration you have to have, you know, trying to run this live on a computer where you can move around quickly without dropping frames, which when you're wearing virtual reality, that leads to some motion sickness. And then also, given the consideration that when you're doing VR, you have to render two cameras at once rather than just the one for your screen. You have to do one for each eyeball. So you're effectively doubling the demands on your machine. So that was kind of the why of what we did. And I'm going to give it back to Jonathan at this point.
Okay. There you go. Thanks. All right. If you start looking at the advertisements and you look at the little videos that you get on YouTube about 3D photogrammetry, about 1, 2, 3 Catch, even getting into some of the remake and some of the other software packages, they make it look really easy and really fast. But the truth, it does take a lot of post-processing. It does take a lot of understanding sort of the geometries, and it does take an opportunity, unless you have really strong computer powers, a reduction in that to make it feasible and make it workable on my desktop or my laptop that I can carry with me onto the site. But with that, there's a lot of drawbacks. One of the biggest drawbacks that we found is just simply the size of the files and the number of photographs that you can upload reasonably. So if you're working in the field, and for us it was, I think we had a total of 238 images to create just the musala, the prayer hall. It took about 2 hours to upload because we had a very slow internet connection. But then we were able to post-process it on the, or process it on the cloud. So we came back in 6 hours, and we had the basic geometry and the basic model created. It did take about 20 hours of post-processing back at the lab to get it into the state that you saw there, that Chris was zooming in and out of. If you get into larger complexes and you still want a certain level of detail, and you want to use these small photo sets, you run into the issue of trying to piece things together, and doing that in a Rhino or some other type of software once you sort of pull them all together. Another limitations that's really quite important is this idea of surfaces. So this is actually one of the airplanes that Chris flies. So when he was sort of first trying this out, this structure for motion algorithms have a hard time distinguishing between surfaces and materials that don't have any distinguishing features. So in this case, particularly when they're smooth, particularly when they're reflective, and when they're monochromatic. So in the mosque, where you had very similar, the squinches, the quarter domes, the fact that that calligraphy was unique was critical to the success of this project. But where you have long white walls or long surfaces that have not a lot of detail, it becomes more difficult. I think one of the solutions that Chris has come up with is Post-it notes, different colored Post-it notes, putting them in several places to try to distinguish them. But what ends up happening is you get holes and voids where the software isn't been able to process this. The idea of repetitive features, this is the 12-sided fountain that's outside the mosque. So outside, they have a fountain outside of a mosque where you wash before you enter for prayers. And this was a perfectly symmetrical around with 12 surfaces that the software just couldn't distinguish. And so one of the challenges we ran into here is you get very, very distorted geometries because the software can't distinguish one photograph from another. One of the things we also forgot to mention a little bit earlier is the goal of having each point found in at least 3 photographs is really critical as you're doing this. But when the computer can't distinguish which points come from which surface, you get very, very distorted geometries. So as much as there are some real advantages to this in terms of very, very quick on-site data collection, by using the cloud-based processing, you're minimizing the need to have powerful computing power at your location or back at your offices or your labs, and then being able to take those geometries and then manipulate them or reduce them as you see fit. There's also some limitations in what can be done on these larger scales, photogrammetric processes. So, thank you.